understand what we're supposed to do. I'm also going to do the recording for the video. I remember last time I was not able to record. In fact, my live recording have had issues, but yesterday I was able to address most of the issues. So you'll be able to see my recording maybe after tomorrow, because I've noted it's taking time to prepare the video. But I'm sure after some time we'll be able to get the video of this class. Actually, the audio recording, I'll just have an audio recording. I want to put off the webcam so that we're able to save the bandwidth. Remember, some of us, I know, we are coming from areas where the network is not very good, including me. Sometimes it misbehaves. But let's see how we can do it. And I hope we are going to have a successful interaction. Thank you very much. I hope you can still hear me. I hope you can still hear me. Okay. Hello. Yeah, Catherine Buva is saying she can't hear me. Catherine, I don't know what the problem is. Gashie, you can hear me. George Waero, can you hear me? Yes. So maybe Catherine Buva, you need to find out what the issue with your earpiece. Otherwise, majority of us are saying they can hear me. Maybe the others can confirm they can hear me before I begin, because I want to start now. I want to have everybody on board. I don't want to leave anybody behind. Mudhini Dungwa, you can hear me. That is good. Who else cannot hear me? Who else cannot hear me? I want us to move together. So it's my wish that everybody can hear me now. As I said, today I want us to talk about database architecture. Database. I also want us to talk about schemas and instances of databases. And these are more concepts. Last week, I don't know how many were able to review my audio recording for lesson 3. I don't know how many were able to see my recording for lesson 3 or topic 3. Otherwise, in not topic 3, sorry, topic 2. In topic 2, I discussed or I introduced a number of concepts. Although you are not able to see the screen, but from the audio recording that I did and shared with you on the platform, I introduced a number of concepts. Today, I want us to look at more concepts so that as we move ahead, we're able to see how we implement databases and the things that we need to understand before we work with databases in organizations. So by the end of this topic, we are going to understand database architecture, database models, schemas, and database instances. So I'll begin by looking at database architecture. And architecture is simply how we design, implement, develop, and maintain a database. We found that databases are critical information systems in an organization. Therefore, being in a position to select the correct database architecture would guarantee a quick and secure access to the data in the organization. And later we are going to see, we're going to look at database design. And here we are saying that database design depends on the architecture, because there are variable architectures, as you're going to see. A database can be centralized, decentralized, or hierarchical. These are some terms that you're going to see later as well. A database architecture can either be single tier or tier. I know some of us might read as tier. We can use, instead we can talk of tier. So you can have a single tier, as you're going to see, or you can have a multi-tier database architecture. We can also have a multi-tier where you use the M to denote multiple. If the database in the organization is divided into multiple elements that are related but dependent on a number of modules, these multiple databases can be modified, altered, changed, and they can also be replaced. This whereby we have the database existing in multiple tiers. That is, we've said you can have a single tier, you can have a multi-tier. I want us to see how a single tier or a one-tier database architecture looks like. A single tier or a one-tier architecture is simply where the client, application, the server, and the database all sit in one machine. If you are a programmer and you are running a database as part of your programming exercise, you are writing code and you are testing how the database behaves in your machine, meaning everything that you're doing is in one single machine. The client program is in the machine you're using, the server program is in the machine that you're using, and the database itself is residing in the same machine that you're using. We can refer to that as a single tier architecture, or what you call a one tier architecture. So this is when you install the Hello. Sorry for that. I hope you can hear me again. Sorry for that. I had an issue with the audio. Okay. Rashid Juguna confirms that he can hear me. Mike is typing. Okay, Wangui can hear me. Okay, we can continue. I was saying that in a single tier architecture, this is where you store everything in one machine. And mostly, it is the programmers who use this kind of architecture. Because you shall install everything in one machine, then you'll be able to use the client program, the server program, and the database in your machine. So it is in very rare cases that you'll find a business organization using a single tier architecture. In most cases, organizations you're going to see use multi-tier architectures. Then you have a two-tier architecture. A two-tier architecture is normally organized like this. This is where we have a database, okay? And the presentation program running as two independent entities, okay? So if you have, let's say the application program, in this case, a presentation layer running on a client, maybe a PC, a mobile phone, or a tablet. And then you have the database running on a server. That can be considered a two-tier architecture. So a two-tier architecture therefore must have an application program through which you can access the database. In this case, the database is not accessed directly, like in one-tier scenario. Okay. Again, programmers are able to use a two-tier architecture where they can access the database by using an application program. And here, the application program is entirely independent from the database, meaning the application program can run on its own. It can be designed independently from the database, and it can be programmed independently from the database. And technology has improved. Today we have a number of IPs called application programming interfaces that allow a client program to communicate to the database through an application program. I mean, an application program communicates to the database through a presentation layer. And a very good example is the open database connectivity, what we call ODB. So today, most of the databases database management systems, they come with the drivers we call ODB, that is open database connectivity. And through this program, the programmer can communicate to the database using the program. In that case, the program is independent and the database is independent. The good thing about such an organization is that the database can be more secure, or this kind of architecture can be more as the single tier architecture. Then we have, that is a two-tier architecture. We have a diagram here, which you can see. So in this case, we have multiple clients connecting to the database, but there is a program in between. But this time it's a presentation program, not a server a program, like the program we talked about, the ODB program. Then we have a single tier architecture. That was a two-tier architecture. A three-tier architecture normally has three elements. So these are an architecture that separates its tiers from each other based on the complexity of the users and how they use the data present in the database. And this is the most widely used architecture in business organizations. A single, I mean, a three elements or three layers. We have the presentation layer, We have the application layer, that's normally the server program, and you have the database program, that is the database server. So what happens is in this particular architecture is the application layer normally sits in between the user and the database. And the application layer therefore receives commands or services or basically requests from the user through the client program, then communicate those requests to the database. Then the database will issue responses again through the same program to the user. Okay, so in that case, the application layer is the one that is responsible for the communication between the user and the database. In most cases, the application layer is normally a program written by a programmer in the form of a business logic layer. And its work is to process requests that are issued through the client to the database. And through this layer, a number of functionalities can be implemented. That is a good thing about it. So we can implement business processes, functional logic, we can implement constraints, we can implement rules that you want to apply before people can manipulate the data in the database, or before the people can use the data in the database. Let me give you an example of a 3-tier architecture, like the ZTech digital platform that you're using now. Right now, you're using an application, you're using a presentation layer, the web browser, or the big blue button that you're using now is a presentation layer. Then there is a program that is sitting between the database where your information is, so that you're able to do the transaction that you're doing now. You can be able to query your records, can be able to display. Again, you can do activities through that program, because their program contains code that is executed for activities to occur between the user of the database and the database itself. So the application program will contain the processes that must be executed for the communication to occur between the user and the database. That means 3-tier architectures are the most common architectures. You can think about any example. Most of the time, these examples would be 3-tier architecture. I think I've gone through this, that a 3-tier architecture has the database layer, that is what you're referring to as the database server. We have the application, which is the middle layer. Then we have the user, which we call it the presentation layer. And we have examples of 3-tier. Think about large websites on the internet, for example. Given the ZDS platform that you're using now, think about Facebook, think about Jumia, think about other large internet applications. You'll find in most cases they have multiple tiers. You have the user tier, that is the presentation tier. This is normally the application that handles as they issued by the client with the user. And again, responses as they are coming from the database again are given to the application layer before they reach the user. This is describing that configuration of a 3-tier architecture. The client's program, like the web browser, can be a very good example of a client program. The server program and the database in most cases will be in the same machine. But you realize the client does not go directly to the database. You go through an application program that issues the request to the database, and the responses are given to the user again through the same application program. Now, the good thing about these components that they can be modified. You can modify these components independently, and each can be changed independently. That's a good thing about having a multi-tier architecture. And another good thing is that users do not go to the database direct, meaning we can be able to implement security measures through the application program and other constraints that we want to have in our database system. Okay, I hope you are together. Can you hear me? You can type "we are together," please. If you can still hear me, make sure you can see my screen. I don't know whether you can see my screen. Can you see my screen? And can you see my screen? Oh, okay. Can you see my screen? Biko, how are you? Some people are saying they cannot see my screen. Can you see my screen? Can you see the slides? Hello, can you see the slides? Okay, thank you. I hope I'm also clear. Yeah, most of the people have confirmed that they can see my screen. Okay, those are architectures, and I must also say that you can have multi-architectures. Multi means three, more than three architectures. That is more than 3 tiers, sorry, where there are other programs or other constraints implemented as programs sitting between the database and the user. Like, for example, I want you to think about a firewall sitting in between. Think about a firewall program sitting in between the user, the application program, okay, and the database. Or think about a sophisticated system like Safaricom system. In most cases, such systems have very sophisticated architectures because, again, of the nature of the operations that take place in this organization. So when you think about the N means multiple. The N means multiple. We are not limiting ourselves to the architectures. We can have multiple architectures because the idea is to have a database that is as useful as possible to an organization in terms of the operations that the database system is supposed to provide. So we can have multiple programs, we can have multiple applications in between or forming part of the implementation architecture. Now, the other concept I want us to introduce is data models. As you've seen, a database may hide so many things. Like, for example, when you're using the e-learning platform, there are so many things that you don't see. Like, you don't see the processes that are taking place. That is what you're calling data abstractions. You're able to hide details of data storage. You're able to hide details of operations that are taking place. So you find that the database approach or the database implementation is able to hide or provide some level of abstractions where details of data processing and data storage that are not needed by the user are hidden from such users. Therefore, when you talk about a data model, which is basically a representation, we talk about a collection of concepts that can be used to describe the structure of a database that provides the necessary means to achieve this particular abstraction. So we're going to look at structures of databases, and we're going to carry on with this discussion because there are a number of things we need to understand. Like we need to understand the relational model, which have basically introduced here by way of scratching the surface. Otherwise, there is a number of classes that are coming on relational data model. But for now, for the purposes of getting us to understand what models are, I have introduced a relational model. We've got a model, just a number of models that we're going to talk about later. But when we talk about a model, we talk basically about the structure of a database. Now, by structure of a database, we mean the data types. Which data types are there? Are they integers? Are you talking about characters? Because the way you store information in database is again complex. There are a number of issues that need to be addressed. One of them is the data type. Then the relationship that exists between the entities, the constraints that should hold on the data. Now, constraints, I remember I introduced constraints in the second lesson. For example, the primary key is a constraint. Maybe the range of a field could be a constraint, the index. So there are rules that hold on the data. Basically, that's what we're saying. Now, most data models also include a basic set of operations for specifying how the data is to be retrieved and updated on the database. Again, this applies mostly to the constraints. So in terms of what we understand by data models, this is how we define the logical structure. Again, we have the physical structure of a database. So again, these terms will be clear later, logical structure and physical structure. Basically, data models are fundamental entities, okay, that we use to introduce abstractions in a database management system. And data model basically define how data is connected to each other, how data is processed, how data is stored in the database. So we talk about the constraints, we talk about how data is stored in the database, we talk about the data types, okay, the rules, even the relationships that exist between data in terms of the entities for which you are storing the data, how these entities are related to each other. Like, for example, you as a student, you are an entity. You are related to a course that you are doing. Like, for example, you are doing database management system as a course. That's another entity. You are doing computer application. That's another entity. You are a lecturer. Like me, I'm an entity related to you by the fact that I'm teaching you. Maybe Madam Helen Nyambura, who is also teaching you, is another entity. These are entities. And there is a relationship. For example, if a lecturer is not teaching you, he may not see your records, or the lecturer may not see your data, simply because maybe there is no defined relationship between that lecturer and you. But a lecturer who is teaching can be able to see your data, manipulate your data in a way. These are the kind of relationships and rules that we are talking about. Again, you as a student, there are rules that apply on what you can do on the data. This is what we are referring to as the exist, that define how the data, how they process the data, how the data is stored, and how the database. Now, we have categories of data models. As I've simply hinted, you have conceptual, and you have physical. Conceptual, that is basically logical, and we have physical. So let's see. We can categorize data models according to the type of concept they describe on the data structure, on the database structure, that is. One, you have conceptual or logical. This is a high-level data model that provides concepts that are close to the way the end users perceive the data. So conceptual models are terms that describe more closely the way users see and use the data in a database. Like, for example, I know you are my student. That is okay. That may be a bit different from the way the data is stored in the system, the physical storage of the data in the system. So basically, conceptual models describe entities, like a student is an entity, attributes. When you talk about attributes, you're talking about the characteristics of entities, like student, admission number, age, gender. Those are attributes. Then relationships, we are talking about associations between the data elements, like a student is associated to a unit or a lecturer. Those are relationships that exist in the data. And you see, we need to clearly define this concept, or we need to clearly see as users of the data, how the data elements in the database must be organized for that data to be useful. You can imagine if you're not able to, let's say, register a unit database management system that is taught to a by a given lecturer. If the database does not allow you to do that, so the way we use the data, the way we conceptualize the database system, that high-level abstraction is what we refer to as the conceptual level, or the conceptual data model, which is basically a logical data model. Then you have physical data model. A physical data model basically describes how data is stored in the computer, how the information is represented in the computer, how the information is stored as records, the format of these records, the ordering of these records, the access paths, or the access rules of this data. We search for this information in the database. So, in a way, physical is more real in terms of the data in the computer, how the data is stored in the computer. Then we have a record-oriented view, or the implementation data models. And this provides concepts that fall between the two. It's like an intermediary, like the views that used to view the data, that used to later we are going to talk about views, like later we shall see more of this concept, because we need to talk about views that the users can use to see records from a database. So when we talk about an implementation sort of model that shows the balancing between the views, the users, and the data, that can be termed as a record-oriented data model. And later we are going to see that. Now, this is relationship model, and later we are coming to entity relationship model, because you need to know from aspects of database design, because when you talk about entity relationship models, these are representations that we use to describe the real world organization in terms of how the database is to be implemented to encapsulate or to store this information about the real world organization. Okay. Entity relationship diagram or entity relationship model is simply a representation of the real world entities and the relationships among them. Now, what happens is, you as the programmer of the database, you collect the data from the environment or from the business environment that you want to represent the information in a database. Then you represent this information in form of a model. We call an interrelationship model. So an interrelationship model, therefore, will describe the entity, the set of the entities that you're working with, the relationships that exist between those entities, the attributes for these entities, and the constraints. These are the rules, like how these relationships are described, or the nitty-gritties of how these relationships are described would form part of the constraints. Now, entity relationship model is a very good example of a conceptual design of a database. It's a high-level design, because basically shows how we interpret or how we perceive a database system as the users of that particular database. Therefore, an entity relationship model will contain the entities and the attributes, like a student and the attributes, like age, name, admission number. Those are attributes. Then the relationships between the entities, basically, as I've said, are associations. For example, a student and a unit or a course, a student and a lecturer and a student. Those are relationships that must be defined for us to be able to use the data. Later, we are going to see these concepts, as I've said. For example, you can see this diagram. An entity will have a number of attributes, and then a relationship will exist between one entity and the other. We shall talk about these entities, and then we shall talk about cardinalities, and we shall also talk about how we conceptualize and develop these relationships during our database design class. Okay. Karab, you are saying I'm not clear. Who else has a problem with my voice? Hello? Is my voice clear? Hello? Is my voice clear? Hello? Check my voice. I suspect the problem is the network. It could be network issues. Yeah, the network could be the problem. As I said before, where I am, the network is not very good. So I don't know. In instances where I'm not clear, kindly bear with me, because it is a network issue. The network here we use Safaricom and it's not very, very good. Although from next week I'm planning to use Airtel. We see how it works. Now, as I said, when we talk about an entity relationship model, which is a conceptual model, we have the entity and the attributes, and then you have the relationships. When we talk about the entity, we are talking about the item for whose we want to store information in the database. So the real world item. like a car, a student, a house, a course, a lecturer. These are entities. Then there are attributes, which is simply a set of values from that domain, or a set of characteristics. Like in a school database, a student is an entity. It's likely to have attributes such as name, age, class, unit the student is taking, etc. Not unit, but admission number, sorry, phone number, email address. These are attributes, or these are characteristics. We're going to see these attributes later become they become columns in a relational database table. Then you have relationships. These are the logical association. I think I've mentioned that we need to map with entities so that we're able to use the entities, so that we're able to use the data in the database. Then we have what we call mapping cardinalities. These are normally defined. These normally define the number of associations between two entities. This is basically what we call multiplicities, like like a student, one email, one student, one email address. I'm sure none of you has two emails in the system. You are given one email, one student, one phone number. You may have two anyway, but you can have one student, one admission number, or one student, let's say, one fee record. That is one to one. One to many, maybe one student, many lecturers, many to one, maybe many lecturers, one student. Think about a situation whereby one student is doing 7 units. It will be, these units are taught by many lecturers. So many lecturers, one student, many to many students, many lecturers. For example, like you're doing 7 units or 6 units. These units are taught by lecturers. Each unit is taught by a lecturer. So that is many to many. Anyway, later we shall see how we work with these concepts. We call cardinalities, or what we call multiplicities. A relational model, as you're going to see, normally conceptualizes a database in terms of a table. And most of the databases used today, in fact, almost 90% of the databases used in organizations today are relational databases, in the sense that they store information in the form of a table. I don't know how many of you have used Microsoft Access. How many of you have used Microsoft Access? Maybe you can type. You can type if you have used Microsoft Access. How many of you have used Microsoft Access database? Now, if you have used Microsoft Access database, what do you see about Microsoft Access database? How is the information organized in the database? Maybe you can type. Yeah, I can see Naomi Chipkurui. How is information stored in a Microsoft Access database? You can type, please, or you can talk. Can somebody tell me? You can talk. You can unmute your microphone and talk to me. Tell me how the information is stored in relational in Microsoft Access. Sorry. Somebody can talk, or you can type. The same previous slide. How is information stored in Microsoft Access? Yes, Lennox. You can go on, Lennox.
In Microsoft, in database, okay, information in database, they are majorly stored in a standardized manner. Like the tables are created and they are stored in a simplest objects like structures. So that, yeah.
Okay. So if you're used to Access, definitely you note that information is stored in form of tables, right?
Yeah.
Now, yeah. So I want you to see this model. In relational databases,
Yeah.
information is stored in the form of a table, as you are going to see. Information is stored in form of tables. Maybe Lennox, you can unmute now, unless you want to say something. Lennox, you want to say something? Okay, Lennox, maybe you can unmute so that we can continue.
No, not really.
Okay, let's continue then. Now, yeah, people have confirmed that I can see Zairo saying that information in Microsoft Access is stored in the form of a table. I want to say that information in relational databases is stored in the form of tables. Microsoft Access is not the only relational database. As I said, most of the databases used in the market use a relational model. In other words, they store information in form of tables. Then these tables could be more than one table, maybe a table for students, a table for courses, a table for lecturers, etc. Then relationships are defined between these tables such that we can query the data in the lecturer and associate that data with, let's say, student table. That's the kind of model that you're talking about. And of course, the constraint, like I can see George Waweru talking about primary keys. Primary keys are ways of defining constraints on how you want that data to be organized and accessed from the database. Now, the relational model is the most popular, and it's based on fast predicate. It's based on first order predicate logic, and it defines as n-array elements or n-array relations. Maybe if you want to understand the first order predicate, you can look at maybe relational calculus. If you want to understand the theoretical background behind relational databases, maybe you can read a bit on relational calculus, and then you read on the history of relational databases. You'll be able to understand where this concept of relational databases came from. In this diagram here, you can see we have a table, we have SID, we have SName, age, class, then you have section. Now, SID, SName, age, S class, S section, these are what we call columns. These are columns, and in relational database terminology, columns build. And if seen an attribute is simply a characteristic of an entity. Therefore, if you think about the name column, for example, S-name column or S-name attributes, you realize we have the same set of elements: Alex, Maria, Maya, Bob, Newton. So you realize a column will store a particular value that is the same or that is similar for all the elements. If you're talking about SID, and maybe this is the student ID, that column will store the student ID. It cannot store the name because that column defines elements of the same characteristic. Okay. Then we have tuples. A tuple is simply what we call a record or a row in a table. And then the entire is what you're calling the table, or basically the relation. Okay. Now, these are the main highlights of a relational model, or the main elements of a relational model. You have data that is stored in form of tables, or what we call relations. The relations are normally normalized. Later we shall come to normalization, so that we store atomic values. What you mean by atomic values? Look at S name column. What you mean by an atomic value is the simplest value. In a very good design database, a value should be atomic in the sense that it should not be complex. For example, Alex is an atomic value. You cannot disintegrate, you cannot divide Alex anymore. You cannot divide Alex anymore. But you cannot store a value like Alex Jogona in one cell. If you store two values, it means that database is not well normalized. Instead of having Alex Jogona, you should have first name as a column and maybe surname as a column, so that you store Alex in one column and Jogona in the other column, so that you work with atomic values. Okay. We cannot have Maya maybe Odhiambo in the same column. That will be complex. To make that simple, or to work with atomic values, we make sure that the values are so small in the sense that they cannot be subdivided further. That is what we call normalization, and we shall see that later. As I said, each column contains values from a similar domain or values of the same kind. Each row contains values of a unique, each row in a relation contains a unique value. Take each row contains a unique value. Take this row that has Alex, 1101, Alex 1498. So look at that column. Each element is defined by the column. So under SID, we have 1101. Under S name, we have Alex. Under S age, we have 14. Under S class, we have 9. Under S section, we have A. So each element or each value is defined by the column or the attributes. And then if you want to now make sense of the data, we read the entire row for us to be able to make sense of that data. But basically, if you take one row, a row contains values defined by the attributes. If you take one student like Alex, all those items under Alex are defined by the columns, and these are simply data values in that particular row. Now, the other terminology I want us to talk about is database schema. In any in any data model, it's important to distinguish between the description of the database and the database itself. The description of the database and the database itself. The description is part of our understanding of the database, but this is how the database itself should look like. Okay? Now, the description of a database is what we call the database schema. The description, not the database itself. The Hello, can you hear me? Hello? 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 Okay. Yeah, I'm happy you can hear me now. My audio seem to have a problem, keep on going and coming. So we talk about you've talked about relational database model, basically a data model. These concepts will keep on coming because we shall do more on what I'm introducing now. Let's come to the schema. Hello? Let's understand a database schema. Let's understand a database schema. I hope everybody can hear me now. Okay, let's understand the database schema. And I will say that for us to understand the database schema, we need to be able to distinguish between the description of the database and the database itself. The description of a database is what we refer to as the database schema. And the schema of a database is normally specified during the design of the database. And in most cases, the schema is not expected to change frequently because a schema is simply a representation of the organization of the data in the business environment that we are developing the database for. Most data models have certain conventions for displaying the schemas, and in most cases use diagrams. Later during our database design, because we need to learn how to design a database for an organization, we shall see how we conceptualize the data organization, how the data relationships, and display that information in form of a diagram. And the most likely candidate for this diagram is the entity relationship model that I've already talked about. We shall see entity relationship models like this as a way of representing the data or the description of the data in an organization. Now, so for us to display our understanding of the database representation, we use diagrams. And this is what we call a schema diagram. So basically, a database schema is a structure that represents the logical view of the entire database. So these are, again, a conceptual, as you said before, it's a conceptual level of understanding of the database and simply defines the organization of how the data is organized and how the relationships among these data items are to be defined or implemented in the database. Simply a description, not the actual representation, not the actual implementation, sorry, but the representation. So a schema, therefore, will not only show the data elements and the entities and their relationship, but it also show the constraints that must be applied on the data. So it will define the entities, the relationships among them, and the constraints that detail how the data elements which you are depicting should be how the constraint that is of how this data that you're depicting will be implemented. That is, meaning the entities, the relationships, and the constraints can be represented in the form of a diagram we are calling a schema. Therefore, it's normally the database designer who designs a schema for the database, and then the programmer of the database will use that schema, which is in form of a diagram, to be able to understand the diagram and be able to implement that particular database for an organization. look at this example here. This is a schema diagram of three entities: supplier, parts, and delivery. If you're given Microsoft Access with such a diagram, I'm sure you can be able to develop the database, because the database will have three tables. You have the supplier table, the part table, and the delivery table. The supplier table will have the supplier number, the supplier name, the status, and the city. The part will have the part number, the part name, the color, the weight, and the city. The delivery will have the supplier number, the part number, and the quantity. So look at that. So the supplier number is a primary key, possibly in the supplier table. And then you find that column is still in the delivery table. In this case, it is a foreign key. That means there's a relationship between the supplier and the delivery, meaning we can query our database and see who supplied a given delivery. If you're using the same supplier number in the delivery number, the part number in the delivery, meaning we can query the database. You can know who the supplier is, which part was supplied, and we can know which delivery. Now, can you hear me? Hello? Hello? Okay. That's basically a diagram. Although in this case, you don't show the relationship. So there isn't much constraints that you can see from this diagram. It's simply showing the tables and the tables, that is the columns. And we cannot see much constraints, although we can see the relationships. You can see the primary key, which basically defines a relationship. Now, a database schema can be divided broadly into two categories. We have what we call the physical database schema and the logical database schema. Definitely the physical database schema pertains to the actual storage of data and its forms in the database, how the data will be stored in the files, how the primary keys will be implemented, how the columns will be implemented, the actual representation. So it will define how the data will be stored in the database. So this I expect it to be more detailed than the logical schema, because the logical schema is an abstract. It's a logical representation of the data that will be stored in the database. It simply defines the tables, the views, the integrity constraints, without giving us so much details. So we need to be able to distinguish these terms. So if you have a representation that is almost near the database that you're going to have in the system, that may be described as a physical database schema. But if you have simply the tables, the views, the integrity constraints, the entities, the relationships, this mostly describes the logical schema. Now, what is a database instance? When we talk about a database instance, first of all, we need to understand that we have the actual data in the database at any particular time, but you also need to understand that that data may change frequently. Like, for example, the database we have for you students keep on changing. Like today, I may get a new student and add that his name in the unit that I'm teaching now, meaning that record will change today. Or maybe some of you might come and tell me that you want to change the admission number. We can change. So the actual data in the database keep on changing. Okay. Now, when you add a new column to a table, That's a change. Okay. Now, if we capture a snapshot of the data at that particular time, like now, if I capture a snapshot of the database for students who are doing, or the records of the students who are doing database management system, that is an instance. That is instance. And we are going to talk about an entity and an instance of an entity. So we need to be clear. There is a database instance and there is an entity instance. Those are two different things. But we shall see what is an entity instance later. If you have students, and then you have John as a student, John is an entity instance. But a snapshot of the database at any particular time is an instance of the database. So the data in the database in a particular moment is called a database state, or simply a snapshot, which is basically the current state of the current or the instance in the database, or the instances in the database. Okay, so a database instance is a state of operational database with data at any given moment or any given time. Simply contains the snapshot of the database. But as you said, database keep on changing. If I capture the database of my student now, it may be different if I capture it tomorrow, because it might change, be added today. So that is what we call a database instance. This is another term I want us to understand here, database independence. Okay. Now, a database normally contains a lot of data in addition to the user's data. And I think I introduced this, what we call the metadata. For example, we may store data about data, what we call the metadata, to locate and retrieve data easily in the database. Okay. Now, it's usually rather difficult to modify or update a set of metadata once the data stored in the database. Like now, when I add a new student, I may not update the primary key to be column. In most cases, if my primary key is the admission number, if my index, let's say the phone number, it might remain like that. That may not change, but the actual data changes. Meaning there is an aspect of data independence. Meaning there is an aspect of how data is and implemented database and the actual data in the database. These are two different things. So as the database expands, or as we increase the records in the database, the records change over time so that we satisfy the requirements of users in the organization. If the entire data is dependent, okay, it may become tedious and complex to keep on changing that data in the database. So what database software developers do, they make sure that there is data independence. The metadata itself is a layered architecture away from the actual data, meaning there is a level of abstraction between the logical schema and the physical schema, the physical representation and the logical representation. Okay, what you're simply, the user data is in its own level, okay, and the representation is in its own level. That is what we are simply saying. That is a layered architecture. So that when we change data in one layer, it does not necessarily affect the data in the other layer. Those two layers are independent. When I change the admission number of the student, that does not change the structure of my table. When I change the email address of a student, that does not change the structure of the entire table. It simply means there is independence. When I change the admission number, I don't need to change the entire table. I simply change a value. I don't change the structure of the database table. That is the kind of data independence that we are talking about. Okay. Now we have logical data dependence and physical data independence. Logical data independence, okay, is the logical data independence and physical data independence is simply the way I have described it. The logical data is data about the database, okay? So it will store information about how data is managed inside the database. For example, how the table is organized, its constraints, okay? It's a kind of a mechanism which allows me to define the structure of my data away from how the actual data will be stored on the disk of the computer. Such that when I change the disk, I don't change the structure of the. If I change the structure of the table, I mean, when I change the items in the table, that does not change the structure. Okay? Meaning, there's a difference between the logical and the physical data representations. Okay? Physical independence, again, all the schemas are stored in the database, in the actual computer disk, again, are two dependent things. That means if you are physical independent, if you are physical data independent, it means that we can change the physical data without changing the schema or the logical data. Okay. For example, if you want to move with your table from one media to another, that should not change the structure of the table. That should not change the structure of the table because there is a physical data independence, meaning change of logical device that stores the actual data should not mean changing the structure of the table. The table structure should remain. So as far as we are saying there is the actual representation of the data, the physical actual representation of the data items themselves are independent from the physical actually in the media data. And that would allow us, for example, to move the data from one media to another without necessarily having to change the structure because we have moved, we've changed the media of the data. I've taken almost 1.5 hours to talk about those concepts. I don't know whether you can still hear me. I don't know how much time we have. Hello, can you hear me? Can you hear me? Now, I'm going to provide an audio recording of this class. That again you're able to follow. Maybe for those of us who have audio issues, there are some students who are saying they have problems with the audio. I don't know whether you can hear me now. There's some there are some people who are saying they cannot hear me. Can you hear me? Can you hear me? Can you hear me? Now, I saw a question from Karani Renson, main features of a relational database. Karani, we're going to talk about the main features of a relational model. We are talking about the major components, for example, like the set of relations and a set of domains that define the way data can be represented, basically the data structure. Okay, maybe another feature would be the way the data would be manipulated in that particular database in form of the queries. Okay, maybe the other feature, as we've already talked about, is the integrity constraints, which basically defines the data integrity in the database, as you have already described. Those are some of the features. Maybe other features. Anything that I've mentioned about relational database so far basically talks about features of a relational model, a relational database. And I don't know whether you can still hear me. I've come to the end. This time I've recorded, although with a few hitches here and there. Now, before we conclude, there's a chart you're supposed to participate in. There's a chart. Let me stop sharing the screen a bit. Then I'm coming back. Just don't go away. I'm coming back in 1 minute. Just 1 minute. Now, I wanted you to participate in the chat before you go, and I'll be marking. I'll be marking each student's participation. Why would you choose a database system instead of simply storing data in operating system files? When would it make sense not to use a database system? Now, I want each one of you to participate in that chart. The chart is don't type the answers here. You go back to the interface away from the big blue button.